So our next talk of the morning. Please resume your seats. We will resume talking about that. Okay, so the next talk this morning is Sunhoot from a variety of Stockholm-based places.
No data.
Oh, detail. Yeah. Okay. And you'll be talking about noisy recurrent neural networks.
Thank you. First of all, thank you, the organizers, for the kind invitation. So today, my talk is mainly about machine learning, so almost 100% about machine learning. So almost nothing to do with neuroscience or brains at all. So apology for that if you are expecting to hear some exciting research about brains, but this is not. But if you are into machine learning and how it could be applied to your research in science, it could be useful as well. Okay, so this is about noisy recurrent neural networks. I will explain what this means, right? Noisy, what it means, recurrent, what it means, neural networks. This is the thing that we are familiar with. And this is based on joint work with my collaborators at several places. Okay, so this is to give you some motivation of why we do this, right? So the idea is that we have sequential data. So this data basically, you can think of it, for example, as time series. So so it means that the order of the elements in the data, they are important, and you need to make sure that you get the order right when you try to learn the data. And it has a lot of applications, say in speech recognitions, video captioning, even in image recognitions, where you can think of each pixel as an element of a sequence, right? You can just roll over the pixels in an image like that. So a key question in machine learning nowadays, and in fact in many applications, like what I just mentioned, is how one could model and learn sequential data, right? Think about time series. So recurrent neural networks, so originally there are some type of models inspire motivated in neuroscience, trying to understand how brain works. But nowadays, people also use it to model time series and learn sequential data. So what are they basically? So they are basically networks of neurons with feedback connections. And because of these feedback connections, it's really good in dealing with sequential data. So I'm sure you heard about like feed-forward neural networks, where basically you just feed an input to an activations, and then the output comes up. And in contrast, in recurrent neural networks, we have these feedback connections. And you can think of this as when you unroll it over time, you have this type of networks, where now think the data is really time series, right? So input data is time series. So the x1, x2, x3, you can think of some data at time 1, time 2, and time 3. And then each time you feed in the inputs to the hidden state that we did not hedge. So at different times, you have different hidden state corresponding to time. And then also you get output y here, y1, y2, and so on. So this is a basic schematic of a recurrent neural network. Okay, so let me just skip over this because it's not so helpful for now. So let me just give you a bit of a framework behind machine learning for using recurrent neural networks. So to do machine learning, we need data, right? So here we focus on sequential data. So again, things about time series. So you have a pair of, you have a number of pairs of input and labels. So let's think about classifications, right? So this input a time series. And so like that, and then the model, so we focus on recurrent neural networks. So basically, mathematically, it looks like this. So again, H here is the hidden state, and X is the input, right? So we basically pass the input to the activations. So typically, this is like non-linear functions in both the hidden state and the input X. And then the output, for the output, you apply some functions g, typically linear or it can be non-linear, of the hidden state H. So this is how it looks like mathematically. For example, the activations can be chosen to be just hyperbolic tangent, which is the most standard choice that people use for machine learning. And the output function g is just linear in the hidden state H. And here we have some parameters that we want to learn, right? So these are just connection matrices, the WHWX, and there's a bias vector as well. And then this matrix WY for the output layer. So this is how it looks like. And then to do learning, we need to specify a metric, right, to measure how good the model is. So we need to pick a loss functions and minimize it. So basically, we do some sort of optimizations to find optimal parameter data using the data that we have, basically. So now to motivate noisy recurrent neural networks. So now we understand what recurrent neural networks are. So how we come up with this idea of noisy recurrent neural networks, right? So okay, from the equation just now, these are the equation for the outdate equations for the hidden state. We are going to add a leaky term like this. And then are going to add noise. So for now, here, this is just additive Gaussian noise, just to keep things simple. And if you look at these equations, this is nothing but certain discretizations of a stochastic differential equations. So basically here, you can link discrete time formulation to continuous time. And so now in the continuous time, instead of just the Gaussians, you have a Brownian motion that drive these SDEs. Okay, so it turns out that we can, so this is just one example. It turns out that one can do things at a more general level by just considering a very general class of SDEs. So this is very general. So here you have a F and sigma. So F is a drift terms, sigma is a diffusion coefficients. And here again, we have a Brownian noise. And we can just look at this and try to come up with different architectures for the recurrent networks by simply picking different type of numerical discretizations. And so if you think about this, this is really, so without this term, right? So this is completely deterministic. And with this one, you basically add these perturbations to the hidden state. So what's the benefit of doing this, right? Why we start with continuous time? Well, there are three perspectives to think about this. So from the point of view of design, so sampling from this continuous time model will give us different type of architectures depending on how we discretize the equations. And from the modeling point of view, in reality, this time series, there might be continuous in time in nature. So it's natural to also have a model that is continuous in time. And from analysis point of view, there are a lot of tools and techniques that we can borrow from the continuous time theory to do analysis and also gain some insights. So now there's questions here, right? So I started with something really completely general, just SDEs with general drift terms and diffusions. But to do things, you have to start with something, right? So how to pick these drift terms and diffusion terms. So here we choose the drift terms to be basically a sum of two components. One, the first one is a linear term, so linear in the hidden state. And the second one is a non-linear terms that looks like this. So here again, A, W, U, and B, these are the parameters that we are going to train. And for the diffusion terms, we are going to take them to be a sum of two components. The first one is additive noise, and the second one is multiplicative noise. So here, epsilon is just think of it as some small parameter. So because you don't want to add a noise to, a noise amplitude that's too big, right? So you want to work with small noise amplitude. So epsilon would be small, and sigma 1 and sigma 2 is just the weight that you put to this different type of noise. So if so during training, we are going to basically inject noise in this way, right, by considering the diffusion term. But during the inference time, we are going to set epsilon to 0. So in this way, you can think of like injecting noise into a hidden state during the training as some sort of stochastic learning strategy. And yeah, as I said, from the continuous time equations, right, we can discretize it and end up with different type of architectures. But for this talk, we are just going to focus on the simplest discretizations that you can think of, which is just a stochastic analog of the forward Euler method. So again, if without this term, we will recognize that this is just a simple forward Euler. So delta M is times that. And then, of course, now that we have SDEs, we also need to take care of the noise term. So here we have square root of the step size. And psi M is basically just some IID Gaussian vectors. And you can show you have a nice convergent property when the step size delta goes 0. This thing converges to the continuous time equations.
Question here.
Yep.
The interpretation that you do for your SDE is always a Stratonowicz, right? If you discretize it like this.
No, this is for Ito.
This is
Yeah,
Ito
so
one.
Ito convention. Yeah.
Okay. It was the other one that should have this extra 10.
Yeah, for now, I think everything will be in Ito convention. But of course, you can convert it to Stratonowicz if you want to. But yeah.
The slide before you introduced noise as with two parameters. One was proportional to the activity of the network, so to the output of the neuron, right? So it's a noise that is bigger if the output of your unit is larger, right?
Yeah.
So but are you going to give us some intuition why introducing the noise like this, or?
We just want to make things a bit like more like flexible because you can fine tune this sigma 2 to see which one, how they affect the result. So just to make things a bit like more flexible. So that's why we have both this additive and multiplicative. And yeah, so
Okay, no, I
does it make
see,
sense?
it's to have both.
Yeah,
okay,
both actually.
types of.
Yeah, you can tune the sigma 1 and sigma 2.
Okay, yeah, nice. Now I see, thanks.
Okay, so we are going to just stick with the simplest possible digitization scheme. And okay, why not higher order integrators? Because, well, they're more expensive. So that's why we're just sticking with this for now. Okay, so just to give you some overview of the results. So intuitively, so why we think that inject noise could help with learning time series, right? So our motivation is really about learning time series that are correlated with noise. So in real life, time series are not always perfectly clean. So sometimes they can be correlated with noise. So think about like images, right? So we have blur images, and you still want the classifier to do well, right? To be able to recognize the image, even though it's really blurred, right? So this is the thing that we care about. And the whole point of injecting noise into a hidden state is that doing this will improve robustness of the model to this type of noise in the data. So this is high level idea. And here we provide some theory to understand this basically. So the rest will be very technical. There will be a lot of equations, but the intuition is what I just told you. So the idea is that how to study this, right? So we have a noise term there. So it turns out that we can do some sort of perturbation analysis in the small noise region. So when the noise amplitude is small, we can do some sort of Taylor expansion, right? And then see what happened. And okay. So after doing all this study, it turns out that adding noise basically has some sort of like implicit regularization effect, which reduces the state-to-state Jacobians and Hessian or loss functions. And this has been shown to promote flatter minima and bias the models toward more stable dynamics. So this is a bit more technical, but I'm going to explain later. And also injecting noise will help to select classifiers with large classification margins, which will lead to more robust model. So again, this is the result that there's some theory behind all this, and I will show you later if we have time. And we can also study stochastic stability for the SDE, so finding conditions under which the dynamics is stable and so on. This I will skip. And then I will focus on the empirical results. So how this can be applied to data, right, to see the usefulness of injecting noise. Okay, I will see all this. So I will just focus on this for now. So if you focus on the small noise amplitude regime, as long as it's small, you can do some sort of perturbation analysis to see what is the effect of noise injections. So it turns out that when you do this, this is the result that we have. So some notations, so this will be important. So, okay, if you consider the corresponding unperturbed systems, and if you basically take the partial derivative on the right-hand side here, we have this so-called state-to-state Jacobians that we call JM, and then importantly, phi hat, which is a product of these state-to-state Jacobians. So this is a quantity that will appear later when we do the analysis. So this is a theoretical results. First result, basically, so what's the effect of injecting noise? So we can see that by doing this type of perturbation analysis for small epsilon, then on average, the loss functions is equivalent to original loss functions plus some order epsilon square term here. So there's Q hat and R hat. And because the step size for the discretization is small, the R hat will be the dominant term here. So if you look at R hat, there's this term here in blue, right? So trace of some quantity. So remember we talked about phi hat, which is the product of this state-to-state Jacobians, and which else is the Hessian loss functions. So this means that by injecting noise, right, you are trying to implicitly minimizing this state-to-state Jacobians, product of state-to-state Jacobians, phi hat, and also the Hessian or the loss functions. So from this type of analysis, you can see what are the effects of the noise injections. So again, basically, right, it implicitly reduces this phi hat and the Hessian and the loss, so this is the first result. And you can see from, if you do simulations, you can see that indeed, if you use noisy RNN, the corresponding Hessian landscape is smoother than the one without adding noise. So this is just to verify what we see in theory. Let's see how much time we have. Okay. So, so here we are going to focus on classification types. And so let me just this. Okay, there are a lot of things going on here, but I just want to say that so from just now we see that injecting noise implicitly reduces this state-to-state Jacobians and also the Hessian loss, right? And it turns out that if you trust me, right, one can derive some technical result that try to study classification margin. So in fact, you can find a lower bound for the classification margin, and the lower bound looks something like this. So just ignore all the technicality here. The important thing here is that this lower bound is inverse, right? So it's 1 over these two norm of the phi hat. So remember that this phi hat is the product of the state-to-state Jacobians that we see just now. So if you inject noise, this implicitly try to minimize this phi hat. So trying to make phi hat small. So 1 over something that is small is big, right? So it means that this lower bound, right, will be bigger if you inject noise. So from here we can see that noise injections implicitly also will increase the classification margin in this way. So let's skip this. So this is the thing I want to focus on. So sure, we have all this framework and theory that show all these benefits of noise injections into the hidden layers, a hidden state of the RNN. And can one really see this in practice, right? So here we have 3 types. So first one is the order pixel by pixel MNIST. So I'm sure maybe all of you here know about Emily's classification task. So basically, you have images of digits, and then you want to classify the digits, right? So here, this order pixel by pixel task is that we basically sequentially present all the pixels in the image to the RNN model, and then use a final hidden state to predict, right? So the probability of the membership probability of the image, basically. And as I said just now, we want a model that do well, right? Even if the input data are perturbed. So here we construct different type of data perturbations and see how effective our model can do, right? So the first one is additive white noise perturbations. Basically, you just add white noise additively to the input data. And then second one, we have salt and pepper perturbations. So basically, they emulate defective pixels that result from converting analog signal to digital signals. And the third one is the most challenging type of perturbations, adversarial perturbations, where these are basically worst case perturbations, maximizing the loss functions subject to certain constraint on the perturbations. So this is the most challenging one. And now we want to see how well the model could do against this type of data perturbations. So these are the results. So if we compare with other state-of-the-art recurrent neural networks out there, so our model here at RNN, the one where we inject the noise into hidden state. So for clean data, the test accuracy is comparable. But if so this sigma and alpha, so they measure the level of corrections in the input data. So for more corrupted data, you see that our model performed better than the other recurrent models. So this shows the benefit of noise injections in improving the robustness of the model to these data perturbations. And we can see the same thing for the other tasks, permuted MNIST. So for the permuted MNIST, instead of presenting the data in the original order, you present it. So you first permute, randomly permute the order of the pixels and then present it to the network. So this permuted MNIST task is more challenging. And for this one, we also see a similar result that our model is more robust to the noise in data. Yeah.
Are the perturbations applied only to the test set or also to the training set?
To the test.
Only to the test.
Yes.
And maybe the fact that it works better than the others with white noise, I'm not so surprised.
No, wait. To both actually. So it's like you have a you basically have a training data and you basically perturb, and then the test is also the same.
Okay, both.
Yeah, both.
Okay,
Yeah.
thanks.
So
Okay,
sorry. So this is one.
I have a question, like when this permutation, you did this permutation on small number of pixels, right? Because if you have one, I can permute it so it becomes 0. No. So what does this mean that you I'm just curious, permuted?
Like you permute the order of the pixels. So like you have x1, x2, x3, right? So maybe now you have x2, x1, x3.
But then I can, take, by doing this, I can change 1 to 2, right?
1 to 2?
Like, you're right, if you permute pixels.
Yep.
Suddenly you can change these.
Yeah, the pixel values, you mean? Like,
exactly.
Yeah, sure, yeah.
I think the question is, what percentage of the pixels do you permute? Is it all of them?
All of them. Yeah, and then choose, yeah.
Is it the same permutation to everyone or different permutation for each?
Random permutations.
Random permutations.
Okay.
Yeah. So
So I have to continue here. So imagine it is kind of possible that 1 and 2 have the same number of black pixels in a 28 times 28 thumbnail, right? So I could make a permutation, if they do have the same number of black pixels, there is a permutation that makes 1 into 2. And you still want to classify 1 as 1 and 2 as 2, even though I could have permuted it to look into 2. So the task is kind of confusing.
Yeah, I understand, but this is like one of the benchmark tasks that people use for this type of like
So what
sequence
was the logic?
it's more challenging.
But do you permute, like, you have one permutation for all your images, and is always that same permutation? Or is it one for each of the?
It's always the same, of course. I mean, you cannot be,
Ah, okay.
because otherwise it doesn't make sense.
I was afraid.
Okay. It's a random computations, but you apply it the same way to all.
Okay. Now it makes sense.
Otherwise, it doesn't make sense too. Yeah. Okay, good that you asked. Okay, so the same thing for when we have adversarial perturbations for the input data also do very well. And this can be summarized nicely in these talks. Yeah, so basically, again, we see that even if you have perturbations, different type of perturbations in the data, the test accuracy produced by our model is better than the other models. Okay, so third task is, okay, this is not so artificial. So this is real data, ECG data. So here we want to basically classify either it's a normal or abnormal heartbeat, right? According using the data. And again, we see similar good performance of our model. So again, okay, for clean data, it's about the same accuracy, but for noise per two like ECG time series, our model is clearly better than the other models. Okay, so let's see how much time. Okay, in conclusions, so here basically we focus on the continuous time formulations, and then from the continuous time formulations, we can choose discretizations, and then we use this as a stochastic learning strategies because we inject noise into the hidden state. And it turns out that you can study a theory and also verify this experimentally that doing this, right, injecting noise into the hidden state does improve robustness of the model against different type of data perturbations. And yeah, for the theory, we study the regularization effects. So what are the effects of these noise injections? And then we show that it does promote classifiers with large classification margin. And I show you some empirical results which agree with what we think about. And it turns out that so doing this type of noise injections, you can, so here I focus on recurrent networks, but you can also think about other type of networks like feed-forward, convolutional, attention, and so on. So it's different type of networks. And if like the simple idea of injecting noise, right, to say input data or hidden state or activations. So this simple idea of just injecting noise can help to improve the robustness of the model to improve perturbations, which is really nice here. Yeah, so with that, I'd like to thank you for your attention.
Questions?
So you showed that the optimization problem in the presence of noise approximately corresponds to applying a particular regularizer. Did you try actually explicitly applying that regularizer to the problem without noise and check how that performs?
Yeah, so in fact, there are a series of papers that try to construct these explicit regularizers. So these are, so now how they do this, right? So you have the original loss functions, and then you basically handcrafted certain like additional objective, and then you just add it to it.
Right.
So usually people use like two norm for this, like Tijuana regularization or something like this. So, and also like they also like two norm of the Jacobian of this like hidden state with respect to the input. So this has been shown to give similar benefits. So it can also improve the robustness of the model. But here we want to say that by considering like stochastic differential equations, where the noise is already built in the model naturally, and so what's the effect of this, right? Implicit effect of doing this, like adding noise there. So it's linked to similar effect of improving robustness of the model.
So you get better results actually adding the noise than using your theoretically derived
Yeah.
regularizer.
Yeah, basically. But maybe the amount of regularization is different depending on how you pick the regularizers, right?
Mm.
So here it's built in implicitly. So yeah.
Because the regularizer would add a bias, right? Which the noise, because the noise doesn't add any bias to your.
The noise implicitly regularize the model.
Yeah, but in a
so-
way that doesn't induce a bias, right? Because the regularizer, you're adding a regularization term will, I mean, it's going to make it more robust, but you're also adding a bias to your
Well, any regularization is adding a bias. That's what regularization is, right?
regular. Yeah, but with the noise, you're not doing that, right? You're not adding any bias.
Well, approximately, it's similar to using that regularizer that was derived theoretically, I suppose.
Yeah, but I'm thinking.
And it's
that it
also
could
doing
be-
something else. That's some kind of residual thing that we don't really know.
But wouldn't it be better because it's not this? It's not you're not adding like a specific, because the noise, it's like the mean is 0, I guess, and then you just add different. Every time you're adding a different change to your data, so would it give you that bias? Maybe it's
I'm not giving the talk. I don't know. I mean, the expected effect on the parameter vector is not 0, even though each
Right,
individual
okay.
noise
It's still-
input is kind of pushing you in a random direction. Right, because it's pushing you towards these particular solutions that have certain properties in terms of the matrix representation.
I mean, you have to think about things on average, right? Because I mean, they are random perturbations.
Yeah.
And you want to study what happened, what are the effects of this on average. So on average, it does this. It gives you this type of regularization effects. I don't know if that makes sense. So
Is it somehow similar to a dropout strategy because it's some kind of noise added to an internal layer?
yeah, I think like people, you can think of it. I think that there's a bit of connections, although it's a bit vague, like connection between dropout and like stochastic training, because you randomly draw some like connections, right? Basically, so yeah, there's some connections, but it's a different procedure, I would say. But yeah, it has it's similar effects. So
Questions?
So in practice, when you do the MNIST experiments, do you have to increase the number of epochs significantly to kind of average over the noise?
no, like you don't have to. Like I think like we use like 200 or something epoch. So it's pretty standard. Like you don't have to don't have to change that, I guess. Yeah.
Any more questions?
Uh,
Good.
And how does it compare to the added noise to the input? But because when you add noise as a data augmentation strategy, at the end you have some like noise in your hidden layer. Does this noise directly in the hidden layer has better distribution? Why is it better to add it there and not at the beginning of the network?
Yeah. The thing is, people have already studied this, so that's what we are not doing here. We are adding noise to the hidden state instead, because there are prior works that already studied this, right? Inject noise into the input data itself. Here will show that injecting noise into a hidden state, you could get similar effects. And it's more general as well, because if you think about case where you inject noise into both the input and also hidden state, right? So, and in fact, talking about data augmentations, we have a paper basically that use this type of noise injections to come up with a new data augmentation scheme. It's called a noisy mix, if you are interested in So basically, the idea is that we take a pair of input data and then we linearly combine them. So it's a convex combinations of this input, and then after that we add noise on top of that. So yeah. Anyway.
Anyone else? No? Then let's thank you for coming here.